Fantastic. So we've had a brilliant couple of X-logs to kick off this quantum morning, and now it's time for our first panel. I'm Nicole, and I'll be your host for this quantum panel, where we'll discuss no hype, will quantum change our world? And to debate just that, please join me in welcoming Markus, Esperanza, and Pep. Beautiful. So to kick things off, how about we start with a round of introductions? Markus, maybe if I hand over to you first.
Thank you. Great to be on that panel. So Markus Pflitsch, I'm a quantum physicist by education, worked at CERN before I left the space for more than 20 years to do corporate finance, investment banking, M&A. But 4 years ago, wanted to combine my passion for quantum actually and my finance background to commercialize on quantum tech. So I founded Terra Quantum, which today is one of the larger quantum tech companies globally.
Okay. So Pep Martorell, wow, it sounds really good. Also bachelor in physics, but a PhD in computer sciences, a long track experience in managing scientific institutions, and since the last 5-6 years, associate director at the Barcelona Supercomputing Center. So HPC, supercomputing, quantum computing is something like a continuous today. So let's gonna discuss it.
And I'm Esperanza Cuenca. I'm head of strategy and outreach at Multiverse Computing, which is the largest quantum software company in Europe. And I spent most of my career in finance and also strategy consulting. And earlier this year, I decided to fully dive into the quantum realm as I see quantum technology a driver to move our societies and economies forward.
Fantastic. Well, I think we're going to be in for a real treat this morning. And finally for myself, so I'm Nicole. I'm a consultant at McKinsey Company, but as I think many of our panelists, I also have a background in physics by training before doing mainly both quantum technology but also sustainability work within McKinsey. So to kickstart us, since the panel is called No Hype, I would love to know what's one of the big quantum myths or hype that you would like to demystify. And perhaps, Pep, we can start with you.
Okay, I think it's good to begin to start talking about hype. We've been managing for the last 20 years the Mare Nostrum computers. Many of you know it in a very nice place, so a lot of people coming to our center every year to visit us, around 20,000 people per year. So 4, 5, 6, 10 years ago, all the questions after the typical presentation were about AI, big data, things like this. But in the last 2-3 years, all the questions have been always the first question after your presentations were about quantum computing. But not only were about quantum computing, the question typically is, what are you going to do with this fantastic computer if this will be useless with the coming of the quantum computers? And then you have to take patience and spend 3-4 minutes to explain that, no, this is not the trick. Quantum computers are coming, but they will not substitute classical computers, blah, 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 blah. But I think it's good to highlight it because some of us, at least I took my PhD in computer sciences and artificial intelligence many years ago, and we suffered what we call the AI winter, probably because the high expectations we create and were not reached at the first time. So I think we need to be very humble, very prudent, very realistic about the real impact of this technology, at least in the field of computing, on the short term and on the long term. If we don't do this, I think we can suffer the same that we suffered with AI many years ago.
Fantastic. Thank you, Pep. And perfect. And so another thing that would be exciting to hear, since there's so much going on in the quantum space right now and there's all this momentum, what is something that has happened recently that you're excited about? Any developments that really resonate with?
Well, in my case, something that actually I was discussing with the team and with Roman, who spoke before, is the recent announcement by Los Alamos National Laboratory, where they have proven with a theorem that using quantum technologies, specifically quantum machine learning or quantum artificial intelligence, there seems to be a less appetite for training data, and this is very relevant. And as Roman was explaining before, our mission is democratizing quantum. We believe quantum is for everyone. And this result also proved, in a sense, something that we were seeing empirically. We were seeing that for some reason, we saw that training quantum neural networks was more efficient. We needed less data. And now we have a beautiful theorem to prove that, which is great in my opinion.
Amazing. Fantastic.
Yeah. Markus?
Okay.
No, I think one of the main things I would like also to highlight, following what Esperanza was saying, and it's something that Markus has explained before, is all the things that have happened where we connect this quantum system with classical ones, right? The idea of having, let's say, the old computers, although old, is a bit excessive maybe, to solve large scientific problems. And then quantum computers being able to solve those problems that, because of the mathematical complexity of the problem, cannot be tackled with the typical HPC technologies. But even having both machines connected with all these four laws well established and being able to tackle complex problems that need the two types of computing, recently have been some papers published on this, and I think this is one of the tracks that will be most promising on the short term.
Yeah, I can only support that. It resonates very much with me, and I think it also resonates with, I would say, the experience curve of quantum tech companies, right? Quantum tech companies are driven by passionate quantum physicists, mostly, right? We are passionate about quantum. We want to have pure and native quantum and run to the clients and say, that's exciting, yeah? But clients have to look at where they come from, and it is, whether they are computing centers or other clients, they have an existing infrastructure, existing supercomputer, high-performance computing infrastructure when it comes to big data applications. And we have to see how, we evolve that going forward, right? And also, what I said, we are going through a, let's say, quantum hardware winter. It will take a few more times until we have really scalable quantum machines which have not so many errors. So we have to not only bridge the NISQ gap, we also have to see what is mid and long-term the truth. And even mid and long-term will not only go for pure quantum, will always integrate it. Actually, that's true on the software side. We'll differentiate which task we do with a classical algorithm, which with a quantum algorithm, and the same is true on the quantum hardware. The supercomputer, the classical supercomputer, will not go away. So therefore, hybrid, I think, is the answer to a lot of questions. Also, to overcome the situation that we just deal with toy problems, right? Corporate clients, target clients, they are bored of, showing them again a toy problem. They want to have meaningful applications which enhance business performance today. And the thing is, and I think that is the learning curve now of the industry, it is possible. Don't be just run with native quantum chips there. Think about hybrid, integrate classical supercomputers, work with simulators, and integrate the early native quantum chips and create an environment where you get an outperformance, and it is possible. And that's the strongest ambassador for quantum.
But I think that's really interesting because the timescale for quantum and when you'll have use cases and value creation, however you want to define value creation, is a really interesting topic. So maybe let's dive deeper there in sort of maybe this short to mid-term first, because I think longer term, there's more consensus for the excitement of the use cases there, but I think this shorter to mid-term, what sort of value creation and the use cases there, I think that's more controversial. And so I'd love to hear from all of you what excites you, what do you think is feasible in that shorter term range?
Yeah, probably I may start with this to also underpin what is really possible already today. And I love to have that discussion because I know that we're all struggling to find the right kind of narrative here. But I can tell you out of practical use case experience. We work for an investment bank Investment banks have a lot of, portfolio optimization things there, e.g. the collateral portfolio. It's a mission-critical classical algorithm. And of course, we find quantum algorithms, and we develop one as well, which optimize that, right? Which are better on a quantum machine. But the thing is, what can you do with that software today? And actually, with our hybrid approach, we could already today reveal a 6 basis points in relation to the portfolio performance improvement that translates into a roughly 200 million euro annual recurring cost save. And that we can do today. Yes, the 6 bips will be 60 bips in 5 or 10 years with a great native quantum chip, but why wait for the 60 bips? Get the 6 bips today, install the quantum software. That is a no-regret move because it's hardware agnostic, and that's our approach, and that excites me, and I think that will propel also the market volumes of quantum applications dramatically forward also in the near term.
And is that using hybrid, or can you?
Yes,
Yeah.
absolutely. That is using simulated qubits enhanced with some native quantum chips, but mainly relying on simulated qubits.
Okay, and which type of hardware?
Well, it's actually classical high-performance computing architecture, which we compose in an IP-relevant manner, e.g. how you access the memory and stuff like this, and we create 40 logical qubits, no arrows, and these are very performant, and we unlock some of the quantum advantage today with it.
This is a very productive field of research today. The idea of taking a classic large HPC system, simulate on this HPC system a quantum computer, and do the benchmark between this simulation and the real use of a quantum computer is an excellent form of learning a little bit more which architecture is better for each scientific problem. Some of the most existing papers today have been written in this field.
Yeah, and on that note, our experience at Multiverse Computing, we worked with quantum and quantum-inspired, and in fact, we use tensor networks. We are fortunate enough to have Romano Rus, who is one of the leading experts in the world in tensor networks. So a tensor network, what it does is that it reduces that the dimensionality of a problem is based on quantum mechanics, and we can execute those on high-performance machines. And this is when I get very excited. We can execute them on GPUs. And I love GPUs for many, many reasons. One of those is that they are super efficient. So if you take, for example, a GPU by NVIDIA, which is a leading provider, I'm a huge fan of their solution, and you execute a quantum-inspired algorithm using tensor networks on that, then the results are pretty impressive, and we have some amazing benchmarks validated by our clients. So, and then you can integrate that into the production systems of the client. Because, yeah, I agree, everything, it is not about a P&L, as your colleague was explaining before. And it's all about the intangible value, that's true. And you have to balance that at a business level with the slavery of the P&L. So proof of concepts are not real until you integrate in production. And I also believe that at some point, you can capture value from these quantum-inspired algorithms. And then my guess is that the integration with existing high-performance computing and GPUs could potentially be easier than the integration with a pure quantum machine.
Yeah, I would like to highlight the idea about the quantum-inspired algorithms. It's been something like a change of paradigm for many of the classical HPC centers here, because 10 years ago, we just managed a CPU-based machine. A lot of CPUs there, the typical algorithms for numerical simulations, fluid mechanics, etc. A few years later, the GPUs appeared. It was something like a change, because now you have to offer to your scientists different type of architectures depending on the codes. Now there's the quantum-inspired algorithms which already run on GPUs, and now it arrives at quantum computers. So for us as an HPC provider service for scientists, this is a real challenge, because we will move just in 10 years from offering one single type of architecture for all the scientists in Europe to offer them a very complex system of machines based on different technologies, and even being able for much of the people to use these machines at the same time, because there are people that are developing algorithms that need to run part of the algorithm here and part there, and you have to organize all the workflows to connect these systems. So this is very exciting from the scientific point of view, but a bit of a very complex thing to manage for us.
No, go for it, Markus.
Yeah, no, it's actually leading me to something which I think is also the future. We in Germany just won the contract to build kind of a quantum cloud environment to access the various quantum devices, right? We'll get a kind of an increasing complexity of various native quantum chips where you would like to have them physically integrated, actually, and then in parallel switch to other classical supercomputing and GPUs, so you have to manage that. And what we do, we created our QMware Hybrid Quantum Cloud platform is something where you can access through a professional cloud environment, actually manage the access to various quantum chips and classical chips. And I think that is the future. So we'll build that for Germany to give German industries access to various devices, and I think that's what we have to think about in the future, also create the infrastructure that we not only have various native quantum chips in some labs around the world, but that there is an overarching kind of structure to access those, right?
For sure. And while we're on this topic of hybrid, I think, as you've said, it's something very promising, and it's soon/now. What are some of the other use cases or examples? Markus, you already mentioned about finance and optimization for portfolios. I'd love to hear from the rest of the panel, what are some examples of something that excites you? Esperanza, please go for it.
Oh, well, it's exciting along various, I would say various fields. And I'm an industrial engineer. So as an industrial engineer, for me, a concept very close to my heart is the concept of a quantum digital twin. This is a concept actually developed by one of my colleagues. And the idea is, all right, so we build a digital twin, which is basically a virtual replication of a system. Google Maps, for example, is the digital twin of Earth. And if we do that for manufacturing process or plant, for example, I'm thinking of a leading manufacturer from Germany that we are working with, and then you integrate quantum algorithms to, for example, to make better quality processes, or so on and so forth, then you have a quantum digital twin, and that is super exciting for a number of reasons, and one of those is, for example, sustainability. We discussed before, and we are working also with leading Spanish energy providers, trying to better predict the weather, so we can better predict the renewable energy production, and that is fascinating. Optimizing the operation of electrical grids, and then, of course, we have worked in finance. We started with finance, and now we are diversifying. And one interesting work that my colleagues did was the simulation of the cryptocurrency adoption. And that was a work done by Ford Bank of Canada. Could that predicted FTX collapse, as I was asked yesterday in Paris? Well, that is difficult to tell, but it's definitely opening the path for future works in this direction.
Probably to add one more out of the energy sector itself, also to differentiate between hype and reality. I think it would be a hype if we would say, well, we can today really enhance the climate modeling task. I think we are not yet there in terms of the quantum hardware. But what we can do today also to help climate is doing more with less energy, so reducing CO2 consumption, and that's quantum for good, right? So we work for a German retail and logistics company having 7,000 trucks. They drive around with 30% of empty miles, right? So it's of course good to reduce the number of empty miles, and we were able to do that substantially by 20 percentage points. It's a substantial reduction and translates for the whole fleet into a almost 3-digit million euro cost save. So it's not only economically wise to do so, but it also helps to reduce CO2 with quantum already today. Yeah, that's not the the ultimate goal of modeling everything, but it's something which we can do today, and we should do that.
If I can add a pair of topics more from the point of view of a center that serves scientists, one is the simulation of any quantum system. Of course, what's better to simulate a quantum system than a quantum computer if we talk about quantum chemistry, etc. And the other field, you talk a lot about optimization. We sometimes talk about this new field called quantum machine learning. This idea of using quantum-inspired or quantum computing, real quantum computing, to solve or to train in a better way machine learning algorithms. I would like to highlight here the idea that you've mentioned before. So what we look for with quantum computing applied to this problem. Sometimes we need to solve a problem that is not possible to be solved by classical computing because of the mathematical complexity of the problem, the MP problems, etc. But sometimes we just look for a better solution for the problem. And this can be a more accurate solution in terms of precision, especially when you deal with optimization. Or maybe we're talking about a faster way of finding this solution. Or maybe we're talking about a way of solving the problem spending less energy. And this is very critical today. Of course, we all know what about the energy prices at all. We are not still there, but probably one of the added values of quantum computing in some problems will be the less much energy this machine spend compared to an HPC classic system. Absolutely.
Yeah. And I mean, it's fantastic that if these are the types of use cases we can see now, then we haven't even touched on longer term and the quantum 2.0 types of use cases. But I'm sure we'll have plenty of more of those types of discussions about full-scale fault-tolerant computing and so on throughout the day. But in order to get there, I think something that's very interesting is quantum talent, and whether you think as industry and academia, we're going to reach an issue of just not enough people and minds to get us there. So maybe Pep, would you like to start us off?
Yeah, I think, let me start with a very simple fact. Looking at the program, you realize that the percentage of the speakers with a bachelor in physics is enormous, which is a problem really for the future because we don't have enough physicists in the world to deal with quantum revolution. Yeah. So probably it's normal that the first generation of developers, users, pushers for this technology come from physics. But we need to go to the next stage. And the next stage necessarily is something about introducing all these disciplines, quantum physics, quantum computing, quantum technologies, in many degrees, bachelors of engineering, mathematics, computer sciences, etc. We really need a lot of people well trained on these technologies for the future, and only based on physicists is not sustainable at all.
Yeah, for sure. And what about you, Esperanza? Multiverse computing, is it something you think about?
Yeah, it's something that we think a lot about, we talk a lot about, and we try to do a lot about. So on Pep's note, something that for me is definitely the way forward is seeing how new quantum masters programs are emerging in Spain. I also must say that Spain is very vibrant in the sense, and I believe we are leading the way in many aspects. And it's all planting now so we can harvest later. And also I think that in the quantum realm, we need all the brain power that we can gather. So yes, of course, we need physicists, we need developers, we need artificial intelligence engineers, and we also need economists, specialists in marketing, and even philosophers and artists. Everyone is welcome to contribute to this quest that we talk, which is democratizing quantum and building practical applications of quantum computing, creating value for our businesses and societies.
And I think this quantum talent topic is something that's very interesting to us at McKinsey as well. And from our research, we've seen that, yes, the number of STEM students, so physics, maths, engineering, and so on, is growing. However, it's not growing comparatively to the rate of tech growth. So quantum, especially in the coming decade, the growth just isn't enough. And Markus, what about you? What's your perspective?
Yeah, first of all, I find it actually quite inspiring, right? I mean, it's not quantum physics, I don't know, a couple of decades back kind of was some nerdy thing. Now it really is there, right? Big time for some hot tech applications. So I think that's really cool. It's a great development. But yes, talent scarcity is the number one thing which limits growth for us. And that's why we are quite active actually to help educate the next quantum talent pool. We have a cooperation with Technikum Vienna where we work and support. We support Technical University Munich with the Quantum Lab, giving some lectures. Actually, we are in discussion here in Spain as well. And I think a lot of other quantum contributors do the same. So I think we all have to work together and create that ecosystem and fuel kind of future talent growth. But I think that's exciting.
Mm-hmm. And so what would be that next step? I mean, here we have a huge collection of minds from industry, both from the quantum side, but also the application side. So it's in everyone's joint interest to kind of solve this problem, to help build that next generation of quantum scholars. What do you think is that critical unlock? What's the next step? You've already mentioned education. Do you think it's exciting younger generations or creating more, university places? Or what do you think is the critical unlock to help build this next generation of quantum enthusiasts?
It's probably like an onion. We have to create several layers, right? I mean, there is, of course, today, some of the quantum stuff we do is really nerdy stuff. We really need a hardcore quantum physicist doing that, right? But of course, we are all try to commoditize it in a way and make it easy, accessible. You were speaking about it, so that really, let's say, standard software engineers can really work with quantum. And I think we are getting there. It will take some time. But I think, therefore, we have to work on all layers, right? So we also need the quantum business developers who can really translate the R&D into a product world and explain it to a customer who is completely still in the classical world. So I think we need all layers, and we need the masters in these things, well, it will happen. So I think we'll see a lot of kind of a mix of kind of quantum engineers arising.
I would like also to add here that another thing maybe we need is to democratize a little bit more the access to these type of systems.
Mm-hmm.
Yeah.
So it's very difficult to really excite people just on the blackboard, And on the following years, I think we will gonna see how easy it will be to access to one of these systems, or maybe to quantum emulators, so classical systems working as quantum computers. But probably this will be another added value for the community if we can open our systems to everybody, at least to everybody conducting a master or a PhD in these disciplines.
Yeah, I agree with that, and I think it's a superposition on everything that we are discussing. Of course, the educational part is critical. We need formal education, so a master's and embedding quantum in all the educational programs. And also education comes in many, many forms. So, for example, reading a book or watching videos from trusted sources or participating in hackathons. All of those are education as well. And particularly hackathons are very interesting to identify people that eventually you would like to invite to join your company and also help you with solving some of your challenges.
I really resonate with that. I think Quantum Hackathon, I remember my first one to this day, and I think that's where the love was sparked. So I really resonate with that.
Yeah, and those are great. And then, of course, democratizing the access to the machines. So, for example, IBM has pioneered this. Of course, some parts of the accessing you need to pay, other are totally for free. And I think it's a great resource and community to get us started. And they are paving the way for others to follow their example.
For sure. And I think this democratizing quantum is something really interesting that's been mentioned several times. And I'd like to lead in the last 5 minutes to something that we were discussing off stage before we came out here, which is the whole topic of, is Europe prepared to become autonomous? And when it comes to quantum technologies, what's your perspective here? Maybe Pep, you can kick this off.
Yeah, Probably as many of you knows, the European Commission together with the governments have been pushing in the last years very strong for this idea of the European sovereignty in technology, whatever you're going to call it, right? In the HPC classic field, it's pretty clear what we need. We need to give to our scientists the access, to guarantee the access to the most powerful machines in the world. And this goes through acquiring some of the most large computers and giving the access to the scientists. I think this is pretty well solved today. We have a big machine in Finland. Next week, we inaugurate a new one in Italy. The Barcelona machine will be ready at the end of this academic course. And after that, it comes one in Germany and one in France. So you can say that the European scientists will have enough HPC resources for the next years to compete with their colleagues all over the world, right? The second problem is far more complex, and it's putting inside this machine as much European technology as we can. This is not easy at all when we talk about chips, communication networks, cooling systems, etc. It's there a pretty clear path, more or less defined, but it's something that it will not be easy, it will not be for the short term, and it will not be cheap, of course, right? If we move to the quantum computing world, I think the European Commission is doing something that it's pretty easy, but it's a good idea, which is, okay, let's first of all acquire a pretty large number of quantum computers and put these computers on the HPC centers with this idea of opening the service to the scientists all over Europe, and they are able to do what Markus was saying before. They will be able to access to a quantum system, to a classical system, or if we're able to build this middleware to something that will be in the middle of everything, or at least you can send there your code that can run a part in a quantum, part in a classical system. This will be fully operative in, let's say, 18 to 24 months. And on top of that, most of the systems, if not every system, will be provided by a European company, which is something pretty new in the technological world, because for the HPC hosting entities, we cannot buy European technology because there's not European technology fully competitive in the HPC classic system. So I'm going to summarize it by saying that the trend there is pretty clear, advancing, making progress through to the European autonomy in terms of technology. In HPC, it's pretty clear, well defined, but it's very difficult to reach it in the short term. I think in quantum computing, we can be pretty optimistic how we will be more or less autonomous on the hardware side, but also on the software side in the midterm future. I don't know if my colleagues are more or less agree, or more optimistic or more pessimistic.
I think that was a very sophisticated elaboration, and I think, unfortunately, I'm not that optimistic, so therefore I'm glad to hear that proposition, actually. But we hear now more and more, even now, in quantum already, conversations about creating some export controls, and I think that concerns me a little bit. I really think that breakthrough technology, Europe, has to own it. We have to own the whole value chain, hardware and software. I think that we have kind of great prerequisites in terms of the research landscape, the talent, also the funding. On an aggregated level in Europe, 7-something billion is good. So we have all the ingredients. I think we have to get our heads together to make it really holistically one European approach as one economy. Otherwise, I think in that heterogeneous landscape, we risk to fail. But I'm a strong advocate. We have to own the whole value chain. And I'd be happy if we manage that, but I think we have to get our heads together and really drive that home as Europe.
Yeah, I agree with that. I absolutely share your views. And also thinking about having transcontinental alliances. There's a very delicate balance between sovereignty and excessive protectionism. So those are not trivial challenges, but I'm hopeful that we will overcome them.
At least I would say that we have the ingredients to take this debate in a good position. Let's say it this way.
Absolutely.
Yeah.
Fantastic. And on that note, thank you very much for a wonderful discussion this morning. And I hope we can continue plenty more of these discussions throughout the next couple of days. Fantastic. Thank you.
Thank you.